Okay, let's finish up our 4.4 and 4.5 examples. I think the last one we did was example 4, and so here's example 5. In a Microsoft Instant Messaging survey, 1,021 adults were asked to identify the most fun way to flirt, and 61 of them chose email. The A part asks what's the probability that one randomly drawn person chose something other than email? Well, the first thing I need to determine is if 61 of them chose email, how many chose something other than email? And I would get that by subtracting. 1,021 minus 61 is 960 people who chose something other than email. And so I want to know the probability if I just put these 1,021 folks in their names in a hat and draw one out, what's the probability that I get one of those who chose something other than email? There are 960 people who chose something other than email out of a total of 1,021 people. So the probability that someone gets that we draw out a person who chose something other than email is about 0.9403 if I round that to 4 decimal places. The B part is asking if 25 different people are randomly selected without replacement, what's the probability that all of them chose something other than email? Well, the probability that just one person chose something other than email is about 0.94. About 94% chose something other than email. But if we draw out 25 people, we want to know the probability that all of them chose something other than email. It says without replacement. So I could start with the 960 over 1,021 times 959 over 1,020 times 958 over 1,019. But this would be very, very cumbersome. If my sample size is less than 5% of the population, then I can use the 5% guideline and not have to multiply those 25 fractions together. 5% of 1,021 is about 10%, and then half of that. Not doing so great in my head right this minute. That's about 51 people. And so, yes, our sample size is much less than that. And so we can use the 5% guideline and not have to multiply 25 fractions together. We can assume that the sampling is done with replacement so that the draws are independent of each other rather than without replacement. So the probability that one person chose something other than email, we've already said that's about not, well, exactly 960 out of 1,021. If we're using the 5% guideline, we can assume that all 25 people have that same probability. So multiply 960 over 1,021 by itself 25 times, or just raise that fraction to the 25th power. 960 divided by 1,021 to the 25th power is about 0.2144. So if we draw out 25 people, there's about a 21% chance that all of them chose something other than email. The C part says if 25 different people are randomly selected without replacement, again, we can play like the draws are independent of each other because our sample size is less than 5% of the population, but we want the probability that none of them chose email. Well, think about what B part was asking here. What's the probability that all of them chose something other than email? If they chose something other than email, what did they not choose? They didn't choose email. Really, the B and the C parts are asking the same question. All chose something other than email means the same thing as none of them chose email. So that's two different ways of asking the same question. And of course, both of those answers are the same. All right. Example 6 has to do with blood types, blood groups, and RH types for 100 subjects. It's set up in a contingency table, and we could count how many people had RH positive blood, how many people had RH negative blood. We could add up how many had type O, that would be 45, or how many had type AB, that would just be 5. And number 6, we're asked if 3 of the 100 subjects are randomly selected, find the probability that they are all group B and type RH negative. Well, I've circled the 2 people who were in group B column and RH negative row. So the probability that the first person is group B and RH negative is 2 out of the total 100. 2 out of 100 is 0.02. Now that's the probability that the first person um, is group B and RH negative. And if I put that person back and draw out another person, then the probability that they're group B and RH negative is going to be the same because I put the first person back. And so is the third person. So the probability that all 3 will be group B and RH negative is 0.02 times 0.02 times 0.02, or you could just enter it as 0.02 cubed. That is 5 zeros and an 8. 0.000008. It's a very low probability that you're going to get all 3 people being group B and type RH negative. That's with replacement. What about without replacement? What's the probability that all 3 are going to be group B and type RH negative? Well, the first person would have a 2 out of 100 chance of being that group and that type. I could have written it as 0.02 again. Without replacement, then the second person only has a probability of 1 out of 99 being group B and RH negative. And if I don't put that person back, what chance does the next person have of being group B and RH negative? There were only 2 in the hat to begin with. I drew out one and didn't put him back. I drew out the other and didn't put him back. There's no chance of that third person still being group B and RH negative. So without replacement, the probability of that happening is 0. Even with replacement, it's very, very low, but without replacement, that's impossible to happen. All right. Number 7, universal recipients are people that have group AB and type RH positive. They can take any type of blood from anybody. So if 3 of the 100 subjects are randomly selected, find the probability that they are all universal recipients. Well, how many universal recipients did we have on that table? Group AB, that's these 5, and RH positive, that's all of these guys. So only 4 in the group are both group AB, and RH positive. If I put all 100 names in a hat and draw out 3 and assume the selections are made without replacement, what's the probability that all 3 are universal recipients? Well, I started with 4 out of 100 universal recipients, and if I draw out one and then put him or her back, the probability that the second is going to be a universal recipient stays the same, and the third as well. So 4 out of 100 times 4 out of 100 times 4 out of 100, or 4 out of 100 to the third power, that is 0.000064. So a very low chance of that all 4 would be, or excuse me, all 3 would be universal recipients. But what if I did that without replacement? Well, the first person would still have a 4 out of 100 chance of being a universal recipient. But if I didn't put that person back, the next person would only have a 3 out of 99 chance of being a universal recipient. And if I didn't put that person back, then the third would only have 2 out of 98 as a probability of being a universal recipient. Now, I've already punched those on the calculator, and I know that that probability is 0.00025. I'm not sure how many zeros I said, but I meant 4 zeros and then 25 after those zeros to the right of the decimal. So with or without replacement, the probability of getting 3 universal recipients is lower. It's a little higher if you sample with replacement than it is without replacement, but either way, it's very unlikely that you would draw 3 universal recipients out of 100 people needing blood. All right, example 8. Use these results from a one-panel THC test for marijuana use provided by the company Drug Test Success. Among 143 subjects with positive results, there were 24 false positives. And among 157 negative results, there were 3 false negatives. Now, I wasn't given a contingency table for this problem, but I could make up one like I've done on, or like I've used on other problems. I could set up a contingency table that had the test results being my my rows, positive result or a negative result. And then I could make my columns be whether the person actually was using or not using. I know that a total of 143 people tested positive. That should be the total positives of those who used and did not use. If you have a positive result, that should correspond to using, but there were 24 false positives, 24 people who had positive results but weren't using marijuana. So those false positives go under the positive results but not really using. And I can subtract to get the number of people who received true positive results. They got positive results and they were using. That would be 119 people, because 119 plus that 24 would add up to the total 143 positive results. There were a total of 157 negative results, and 3 of those were false negative. False negative means that they tested negative, but they actually were using. So I had 3 people who tested negative, but they were using. Those are my false negatives. That means I had 152 people who tested negative and got the correct results. They were not using. Now, I may not have had to make the contingency table for this particular problem. I didn't go on and read what the question was, but I wanted to show you how to extract a contingency table from the information that you were given. Just make sure you understand the 143 is the total positives, not just one of these two columns, and the 157 is the total negatives. And by the way, you could add those and find out you had a total of 300 people who took the test. So the question is, if 2 of the subjects are randomly chosen without replacement, what's the probability that they had incorrect results? The incorrect results were those false negatives and those false positives. So 27 people had the incorrect results. 27 out of 300 would be the probability that the first person had the incorrect results. And if we didn't put that person back, then there would be 26 people left with incorrect results out of 299 total people. And I've already entered that on my calculator. It's 0.0078. So there's less than a 1% chance that if we drew out 2 people, they both had incorrect results. Um, it's a little better than the lie detector test. There's still quite a few people who are getting the wrong results on that test, but not as many people who got the wrong results on the lie detector test. All right. I believe there are 2 more. Number 9 says, consider taking a 5-problem multiple choice test with 4 choices for each answer by guessing. All right, so the test has 5 problems, and each problem has A, B, C, and D as the possible choices. There are 4 choices, only one of the 4 is the right answer. So for any particular answer, what's the probability of guessing correctly? Again, there are 4 possible answers, and only one of them's right. So the probability of guessing correctly on any particular problem is 1/4, or if you wrote it as a decimal, 0.25. How would you get the probability that you guessed incorrectly? Well, there's a couple different ways you could think of it. If one of the 4 answers was correct, then 3 of the 4 answers were incorrect. So the probability would be 3 out of 4. Another way you could find that answer is to say that the probability of being correct is the complement of the probability of being incorrect. If you had a 25% chance of being correct, then there's a 1 minus 0.25 or a 0.75 probability that you guess incorrectly. What's the probability of scoring 100%? The only way you could score 100% is to guess correctly on all 5 questions. The probability that you guess correctly on the first question is 0.25. And in order to make 100%, you would have to guess correctly 5 times. The probability that you guess correctly 5 times is 0.25 to the 5th power, or 0.00098. Now notice on my calculator that came up with an E in it, but I know that 9.8 can't be a probability. Probabilities are always between 0 and 1. So that E reminds me this is in scientific notation. Move my decimal 4 places to the left. That's why I added 3 zeros and then rounded 2 decimal places after that. There's not a very good chance that I'm going to make 100 on a multiple choice test where I'm just guessing. What's the probability of scoring 0? Well, to score 0, I would have had to guess incorrectly every time. The probability of guessing incorrectly on the first problem is 0.75, and I would have to be unlucky 5 times in a row to have made a 0 on the test. 0.75 to the 5th power is about 0.2373. I have a much, much higher chance of scoring 0 than I do of scoring 100. There's about a 24% chance that I'm going to make a 0 on the test. If A is the event of getting at least one correct answer, what is a complement? What would be the complement of getting at least one right? Everything that doesn't include at least one right would mean that they were all incorrect. If I didn't get at least one correct, then I missed them all. And that's what a complement is. So the probability of a complement is the same as my probability of that I would make a 0. The probability that I was going to make a 0 was 0.2373. That's the probability that all of my answers were incorrect. The probability of getting at least one correct. Well, at least one correct is not the same thing as making 100, but at least one correct is the complement of that, the complement of missing them all. So the probability that I got at least one correct is 1 minus 0.2373, and that's 0.7627. So there's about a 24% chance that I'm going to get a 0. There's about a 76% chance that I'm going to get at least one right. If B is the event of getting no correct answers, what does B complement represent? Well, the complement of getting none right isn't getting all of them correct. That's not the right way to think about it. The complement of getting no correct answers is getting at least one correct. And the probability of getting at least one correct, that that's the same as this. That was the probability of getting at least one correct, 0.7627. And the probability of getting, or the probability of event B getting none correct, that was the same as the probability of making 0. So C and D were asking the same two questions, but in a different order. C was asking for the probability of making a 0 and then the probability of making something more than a 0. The D part was asking for the probability of making more than a 0 and then the probability of making a 0. You have to read very, very carefully. Actually, in the whole class, reading is reading carefully is the essential component of doing well in statistics. All right, just to sum up what we've talked about, um, when I'm looking for the probability of A or B, or tells me to add, but I just have to be careful to come up with a total that in which every outcome is only counted once. If I want the probability of brown eyes and then the probability of brown hair, then I can't count the brown hair, brown eyed people twice. And then the word and, probability of A and B, tells me to multiply probability of A and B means that you should multiply the probability of A and the probability of B, but make sure you don't do it, or make sure that if B depends on A, you take that into account. All right, last example, gender outcomes. If the probability of having a girl is 0.4, find the probability that a couple with 3 children has exactly 2 girls and exactly 2 boys. I think in an earlier example, we listed the possible outcomes for gender of a couple who have 3 children. Here they are, you all the way from all 3 are boys to all 3 are girls. Number 1 says circle the outcomes which represent exactly 2 girls or exactly 2 boys. This is exactly 2 boys, exactly 2 boys, exactly 2 girls, exactly 2 boys, exactly 2 girls, exactly 2 girls. So, of the 8 possible outcomes, 6 of them involved either 2 boys or 2 girls. Underline the outcomes which do not represent exactly 2 girls or exactly 2 boys. Well, there are only 2 outcomes that I don't have circled, and that's boy, 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 or girl, girl, girl. Would it be easier to find the probability of these 6 events? That would involve multiplying 6 fractions, or the probability of these 2 events? I think it would be much easier to find the probability of those 2 events. I'm going to say the underlying outcomes would be easier to find. Which of the let's see. What is the probability of the outcome that's easiest to calculate? The probability of the underlined outcomes. We're saying that the underlined outcomes are probability of boy, 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 and not and, but or the probability of girl, girl, girl. The probability of a boy, well, the probability of a girl is 0.4, so the probability of a boy is 0.6. The probability of boy and boy and boy is 0.6 times 0.6 times 0.6, or just 0.6 to the third. The probability of 3 girls would be a girl and a girl and a girl. That probability would be 0.4 to the third. And since I'm looking for the probability of either of these 2 things, I add those 2 probabilities. And I get that the probability of all boys or all girls is 0.28. That's the probability of these 2 events. But if I want the probability with 3 children that has exactly 2 girls or exactly 2 boys, it's everything except for what I have underlined. If I want the probability of everything but what I have underlined, and I've already found the probability of what I have underlined, then I can find the probability of the other outcomes by subtracting the 0.28 from 1. Having exactly two girls or exactly two boys is the complement and includes everything except for all three are boys or all three are girls. It was easier to calculate the underlined probability than the circled probability. So when I found the probability of all boys or all girls, I just subtracted that from 1, and I have the probability of um, a family of 3 children having 2 girls or 2 boys is 0.72, about a 72% chance that the couple will either have exactly 2 girls or exactly 2 boys. All right, that's all of our examples for 4.4 and 4.5. Just look at your assignment sheet to see what the homework is. Thanks.